I actually found plans on the internet to turn your PC tower into a half computer, half coffee machine. It was really cool.
I'd never use that.
So we're moving on from derivatives to integrals. What do you think an integral would be if we just learned all about derivatives? Like after we learned about addition, what did you usually learn about next?
Subtraction.
So it's the opposite.
So it's the opposite of a derivative.
So if you have y prime, you can find y with it.
What?
So if you have like y prime, you can find.
So if you have y prime, you can find y.
Wow, sweet.
Oh.
That's go home to my family. I learned how
Or
to
if you have velocity, you can
I
find
like how that's how we.
position. So we can take what we've learned and do it backwards.
Someday, Ryan, we'll learn how to use
But
it.
obviously derivative was a lot more complicated than addition. So integral is going to be a lot more complicated than subtraction.
Idiot.
It's a harder opposite. There are some differences. So we talked about this question a little bit. What is the relationship between the two warm-up problems? So we discovered that the total distance traveled
Google. These things. Oh, is this 5.7?
6.1.
Oh, just kidding.
Total distance traveled is the same as the area under the velocity curve. Well, the velocity straight line. What if it wasn't a straight line? Velocity
So are you talking a curved line or like a diagonal line?
curve. They actually call any graph a curve, so that's why I'm saying curve, even though it was a straight horizontal line. But what if it actually had some curves in it? What if it wasn't a line anymore? What if our graph
Looked like Josh's bumper.
Bumper isn't bent.
That fender?
It's the side of my car.
What if our
Is
graph
that where Jesse hit it?
Oh, no, it's always been there.
looked like that? Does that concept still hold true if our picture is no longer a straight line? Because I can find the area of a rectangle. Can I find the area of this
To
within
guess,
our with
yes.
any of our known geometry formulas?
I guess.
Yes.
How would I find the area of this then?
I would find the rectangle underneath the curve and inside the curve.
Okay, so Josh says, what if I took a rectangle under the curve? What if I took this shape and I took this rectangle? Is this going to be the exact area?
No, but then you have to let's go the curve. Or let's,
So this is not the exact area. It would give us an approximation. So what did you think you should do next, Josh?
you find the rest of the area under the curve now. You have
Okay.
a little.
What
more
shape
space.
is this though? Do we know what shape this is? It's almost like a half circle, but it's not necessarily a circle. If I drew a circle, let's see if I can get a good. That's really a half circle.
It's an eye.
We covered more of the shape doing that.
Then you have two triangles.
Okay. So Ben says, why not do two triangles? But is that still going to give us the exact area if I do a triangle?
You use an integral.
Yes, we will eventually lead to that. We're still going to be missing. It's hard to see because, we're drawing, but there is a little sliver we're missing. So at this point, we could approximate
Taxology.
the area, but we couldn't find it exactly. So let's say we want to approximate it. We decided I can't find it exactly, but I could use some shapes to approximate it. What's the easiest shape to find the area of?
A rectangle. Square.
A rectangle or a square.
Squares.
Basically the same thing.
Except for one has equal sides, which means you don't have to solve it from sides.
Man,
I'm a mathematician. I'm lazy. I
I'm
learned that
gonna
from my calculus.
bring this up.
You got a
I
point.
cannot seem to draw straight lines right now. Come on, where's why do you do that?
Because it doesn't like you.
It doesn't.
That is so cool how you can do that. Just saying.
Maybe.
Oh,
Maybe
dear.
I can do it.
Ninja-like skills.
No, don't just take one, take two. It has to have a buddy.
Okay, so let's just draw a random shape again that's similar. So we said the best, or the easiest, not the best, the easiest shape to find the area is a rectangle. So if we do approximately what we were doing before, okay, is that rectangle going to give me a very good approximation? No. How can I make that approximation better only using rectangles?
Add another rectangle on
Okay.
top.
Okay, we could. Part of the problem with that is we need information. If I add this rectangle in, I'm not 100% sure what these x values are. Like here I decided on my x value and then just hit the graph at that x value. So let's say we can only draw from the x values. We can't do a y direction rectangle. So 1 wasn't enough.
You broke it.
Did break it.
Congratulations.
Don't hit undo twice. It does something undo.
I just wanted to take the stick. I'm gonna kill my smartboard today. It's been doing this all day. Fine, that rectangle is staying. We'll just use a different color. What if instead I did another rectangle? Let's actually do more than just
2.
2.
Let's do 4 because 4 is better. Except for talking about math. At last I see.
It is. Okay. Now do I fill in more of the spaces?
Yep.
So I could use multiple rectangles to approximate this. What do you think we're going to lead to eventually? Today we're going to just be approximating using
Rectangle.
a certain number of rectangles. How can we make this even better?
Use the little integral across.
We don't know what that means yet. How can I make this better using what we know what it means?
Google it.
What did you say, Evelyn? You can make more rectangles. What if I
Evelyn, why would you do that?
made more rectangles? How can I make it even better?
Add more rectangles.
More rectangles. More. How could we make it
You can
so
send-
good that...
Miss Buskus?
Oh, she's texting me back. I will
She's
look at it
texting
in a second. I am in.
That's a rainbow of stupid.
Oh, I am.
So more rectangles. How can I make this the best possible?
Even more rectangles.
Even more rectangles. How many more rectangles?
Infinite.
Infinitely many rectangles. So eventually we'll get to the point where we can do infinitely many rectangles, and that's really what the essence of an integral is. But today we want to practice doing what? Drawing rectangles is bad. Okay, I'm going to
I'm gonna
pause
go
the
tell my
video for a
little
second
sister.
and... Okay. No, I just paused it. For... Okay. So you are going? Yeah. So when we're doing these particle problems, we're talking about a particle that can only go forwards and backwards. Okay? We've talked about the particle problems a little bit, but it's been a little while. So this particle can only move forwards or backwards, but its graph can be different than a straight line because the speed can change. I can go really fast or kind of slow. Yeah. Yep. Good. So the velocity is v of t equals t squared for time t greater than or equal to 0. Where is the particle at?
0.
At t equals 3, after the first 3 seconds.
Not 0.
So if we draw the graph, what kind of graph do we have? Parabola. So it starts at 0, 0, goes through 1, 1, goes through 2, 4, goes through 3, 9. Now again, this is the velocity graph. So let's say our units are meters per second.
It's pretty fast.
And this is seconds. I guess we could have said centimeters per second. Just picking some random units. So meters per second is the velocity. Seconds is the time. So what did we say will actually give us the distance traveled? We didn't say it would give us position. We said it would give us the distance the object traveled.
The area under the curve.
The area under the curve. So let's pick some rectangles. Okay, let's try 3 rectangles. So if I split it into 3, it's not necessarily going to give me a great approximation. And we can find the area of each rectangle. So how would I find the area of this first rectangle?
1 times 3.
1 times 1. We knew the distance across was 1. And we can find the height is 1 because if you plug the distance across of 1 into here, 1 squared is 1. So 1 times 1, this gives us an area of 1 for the first rectangle. What about the second rectangle?
Do you square both the 4 and the 2 or just?
No, just the 2 squared would give us the height. But how far across? What's the width of this rectangle? 1. From 1 to 2, it's 1. So we have 1 times 4 gives us 4. What about our last rectangle? What's the width?
1.
1 again. What's the height? 9. That's 9. So we have 1 plus 4 plus 9. 14.
Minus some.
So the part, minus some, this is only an approximation. The particle traveled approximately 14 meters, since we were saying meters. And notice units-wise, one of the reasons I like showing the area is just units-wise. If this is 4 meters per second, and this is 1 second, and I multiply those two things together, then the seconds goes away and leaves you with just 4 meters. Because basically we're using the formula, distance is rate times time. It's basic physics. So our particle traveled approximately 14 meters. Where did it start at, though? 0. So what is it? What is the actual position if it traveled 14 meters? 14 meters away from 0, so 14. So the position is approximately 14 meters at time equals 3. Now we said we could make this better though. I want you to take the same problem and this time do 6 rectangles. So how wide are our rectangles going to be this time?
1/2.
1/2 wide, but the height will change. How are we going to find the height of each of these rectangles?
Google.
How would I find the height of this little rectangle here?
1/2 square.
1/2 squared. Why did Josh square it? Where did that come from?
The equation is t squared.
The equation is t squared. So if my x value is 1/2, 1/2 squared is whatever the height is. 1 squared would give us the height here. 1.5 squared would give us the height here. 2 squared. So you guys are going to approximate. I'm going to give you about 3 minutes. So you should have done something like this. I'm not even 100% sure what the answer is. Did anyone?
11.375.
11.375?
Bless you.
Thank you. But what do we notice about this that could maybe help us clean it up a little bit? What does each have in common?
0.5
0.5.
and squared.
Um,
That would work.
yeah, the squared we can't factor out, but we can factor out the 0.5 and just have 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared plus 2.5 squared plus 3 squared. As long as our rectangles are all the same width. That doesn't have to happen. Right now we've been working with rectangles all the same width. So we can basically factor out the width of the rectangle. Just to make it a little easier to look at and work with. So we got 11.375. So that was quite a bit different from what we had before. Before we had 14 meters. Now we have closer to 11 meters. What if the particle had started at x equals 5 instead of x equals 0? Where would our particle be at then?
It would be at 16.
Okay, how did Emma get that? She said 16.375.
She added 5 to the 11.
She just added it. If our particle started 0, if our particle started at 5 and then traveled 11.375 meters, we just finish at 5 plus 11.375. And again, this is an approximation. We're not finding it exactly yet. So there's different ways we can draw our rectangles. The 3 different ways we usually use are called LRAM, RRAM, and NRAM. I don't really remember what it stands for. Riemann sum is somehow associated with this. So the guy who actually discovered this was Riemann instead of Newton. So we're using Riemann sums. So this is a left Riemann sum, but I forget what the AM stands for. Something, maybe approximation method? I don't remember. But a right Riemann sum and a midpoint Riemann sum. So these are the 3 basic approximations we use.
In other words, all I do is make up something like this, and then it could be the bend right sum, the bend left sum, and the bend middle sum.
It could.
That'd be awesome. I could be famous.
Oh, I don't want to do that yet. Okay, come on back button. Why? Go same number of rectangles. Let's say we're doing 4 rectangles for each. So we would draw all of our lines the same. They would all go up the same point. What's different is how we're going to connect these lines. If we're doing a left Riemann sum, we're starting from the left side of the rectangle and drawing from the y value on the left side. So here's my first rectangle. What's the y value on my left side? 0. Okay. So this rectangle starts at 0 and goes over there. So that one actually has an area of 0. What if I do this one? We would start here. So we start at the left. That's why it's a left Riemann sum, is because we're starting from the left side. So this one we'd start at the left. Start at the left. This one's the last rectangle. With a right Riemann sum, we start at the right side. So we would start here. Start at the right. This time when we start from the right side, it doesn't just naturally hit something to finish. We have to know, I want to stop as soon as I hit where the other rectangle would be, and we have to actually draw a line down to connect it. Same thing here. Draw from the right, go down. Draw from the right, go down. And the midpoint is the weirdest one. The midpoint, you're looking for halfway between the left and the right. Oops. Can't do that when I'm touching the screen.
Don't touch the screen.
Back. So midway between is here. So we're going to take from that y value and go to the right and to the left. So midpoint, go to the right and to the left. We're going from the middle. So let's stick with our quadratic. And let's do all 3 of these for our quadratic and see what the different answers will look like. So let's say we can actually just still use this picture. This was our LRAM. Let's say we're just going from 0 to 2, which would make the widths of these rectangles what? 0.5. The total distance is 2. We have 4 rectangles, so if we divide by how many rectangles, we split it into equal amounts. So this one would be 0.5 for the width times the height from the left side. So what's our first height? 0. What's our second height? Oh, I'm going to actually just square it first and write it down, but thank you. If we have 0.25, so 0.5 is 0.25. Usually when I'm doing this in my head, I use fractions instead because I can square 1/2 easier than 0.5 in my head. Plus, and then we have 1, so we went to 0.5, 1, 1.5, then we have at 1 squared, which is 1. And 1.5 squared, that's the same as 3/2, so 9/4. So 2.25. Oops, plus 2.25.
You said 9/4?
9/4. Right? 3/2.
You got it right. I was thinking
9/4. Okay. It's quite possible I got it wrong, so that's why I was making sure. So now if we simplified all this down, we would get 1 plus 2, 3.5 divided by 2 is 1.75. Plug that into a calculator and make sure. Since that was in my head.
Okay.
So you just square the whole thing?
No, I just squared each as I went. So instead of writing 1/2 squared, I wrote 0.25 because that is 1/2 squared. Is that correct? Okay, good. So our first approximation is 1.75. Are you not getting that?
Oh, it added something different.
Okay.
I got that.
Okay. So now we would do the second approximation. We would do our RAM. So it's still going to have the same width of rectangle. It's still 0.5. But what is our first height on the RAM? Instead of using 0 squared, we start with 1/2 squared. So what's our first height if we're starting with 1/2 squared? 0.25. Then we add 1 squared. Then we add 1.5 squared, which we already had when we did LRAM. Plus 3, or sorry, we're only going to 2. 2 squared, which is 4. So if we add that all together, 5, 6, 7.5.
What are you squaring again? I'm sorry.
Squaring each x value, 1/2 squared, 1 squared, 1.5 squared, 2 squared, because that's how we find the y value, is plug in x.
Will it always be 1 squared, or will it change?
It'll change depending on the function. Since we're using the function x squared, that's why it's been squared. But if I did x squared plus 7, I'd go 1/2 squared plus 7. 1 squared plus 7. Yeah. Yeah, we're still using that same function. So if we simplify this down, this should be 3.75. So knowing those two, what do we know about the actual value? It's in between those two, which I think is what Stephanie has said. Okay, our value is somewhere in between those two. We don't know exactly what, but it's somewhere in between. Okay, so then MRAM still have a width of 0.5. Our rectangle's width has not changed because we're doing the same picture for all three. But this time, instead of using 1/2 to find the height, what value am I going to use to find the height? 1/4. What's halfway between 0 and 1/2? So we're going to use 1/4 squared is 1/16. I have no idea what that decimal is, so I'm going to just write 1/16. So then we have to use what's halfway between 1/2 and 2. 1/2 and 1. 3/4. So then we would use 3/4, which would be 9/16.
So weird.
And then we would use what's between 1 and 1.5.
1 1/4.
1 1/4, so 5/4, which is 25/16 when we square it,
1 and 1/2, halfway between.
is 1 1/4. Halfway between 1 and 1/2. 1 and 1.5.
Oh, okay.
Sorry, 1 and 1.5. So then what's halfway between 1.5 and 2? 1 3/4, which is 7/4, so 49/16. So we get 50, 75, 84. I'm going to change my 0.5 to a fraction since all of this is fraction form right now.
So 84/32.
84 over 32, but we could reduce 84 divided by 2 is 42. Yes. So we can reduce, cross cancel, we get 42 over 16, which can reduce again. What divides into both? 21 eighths. Or
2.60.
so that's probably the closest approximation of the three. We know it's somewhere in between 1.75 and 3.75. So that's probably the closest approximation we have. So
Do you always have to do all